Eventually, because I mean, part of the idea, I want to go back to old skills here. I definitely want to throw back to some old calculations. Like I want to do a weighted average by hand today. A couple times actually, because there's a point. I've been talking, like I said, I've been talking to a lot of statisticians as I go through this job, and I try to refine the course and make it more pertinent for what you guys are going to go out and do in your lives. And the more and more statisticians I talk to, the more I hear certain things come up over and over again. Make sure they understand distributions. Yay, good. Yes. A couple of you are like, yes, please make sure they understand that. Make sure they understand what an average is. Good, good. Make sure they understand what simulations look like, or what Monte Carlo simulations are. That's your entire third project, essentially. So I want to throw back, we're so good at using technology now, as far as running the averages, running one-bar stats. I want to throw back to old school temporarily, and then obviously go back to the technology because it saves us time. But I want to revisit, especially the idea of a weighted average, which is what this is all going to be. So, number one, rolling a single die. So this is an experiment. It's like the experiments you do when you were tiny and you plant plants and you do things like playing classical music and yell at them and all that stuff. You know, you see what the results. So you guys just did an experiment. What happened? Each time you rolled the die, you got numbers. What numbers did you get?
It varied.
It varied? How much did it vary?
Not very much.
Not by much.
Between 1 and 6.
Boom! There we go. We can actually give it a range, right? You can't get more than 6. You can't get less than 1 on a single die. Be perfect. Thank you. So essentially, this experiment, we can at least run the data. We can at least run the data, correct? So we can say, all right, data. I'm going to call X column, single variable statistics. X is the number of pips that we saw. If you learn nothing else today, you'll learn the dot on a die is called a pip. So if you learn nothing else today, you know that. You can go home now. So I'm going to make one column for starters here, the frequency column. And we're going to collate our class results. And then we're going to add another column over there, to tie it into what you guys have been doing with your projects. So the results, as Pat said, we could have gotten a 1, 2, 3, 4, 5, 6. Beautiful. Thank you. Let's keep track. I'm going to call each one out. If you got that number, raise your hand and show me with fingers how many you got. Does that make sense?
Yes.
So just, so 1. How many got 1s? And let's hold up the fingers and I'll try to do this correctly. All right, this is not guaranteed. 4, 5, 11, 12, 13, 17. We're going to call that 22, 24, 25, 26, 27, 28, 29, 30, 4, 5, 7. We're going to hope that's close. And it doesn't matter if I'm exact. Doesn't matter if I'm exact at all. Because it matters is, well, you'll see what it matters in a minute.
Okay.
Choose! Oh, Pat, go ahead.
Okay. Is it just the first roll? You said number of pips?
No, the number, how many, so you roll a die.
Right.
And there's dots facing up at you.
Right.
That's how many pips did you see on that roll. So 37 people in this class of, say, roughly 30 people or whatever it is, 37 of them saw 1 at some point in those 10 rolls. So you look at your notes. You have 10 numbers written down, right?
Right.
You put fingers up. How many 1s do you have? How many times did you see a 1 when you rolled the die?
We need to. I didn't understand.
Oh, I'm sorry. Add a couple more in.
Make it 38.
Make it 38. Well, that's easy. That's fine.
Right.
Chances are I counted wrong anyway in the first place. Is everybody clear with what I'm saying? So just look at your data numbers and yeah, cool, excellent. 2s. Let's go with 2s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 23, 25, 31, 33, 37, 38, 39, 44, 48, 50. Love it. 3s. All right, we got 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 22, 24, 25, 29, 31, 33, 34, 35, 36, 37. Excellent. Excellent. Predict how many 4s we're going to get. Just predict. Try to get a guess in your mind. Don't have to say it out loud. Just predict what you think is going to happen with 4s.
39. Oh.
Got a number in your head? That's okay. You say it out loud. It's totally fine. It's all good. And now let's see how many 4s we actually did get. Let's see how close Carly got. I heard 30 something back there. Was it 30?
39.
39, let's see how we got. Let's count right too. We got 6, 8, 9, 10, 11, 15, 20, 25, 27, 31, 32, 33, 34, 35, 36. Not bad, dude. Not bad. Not bad. Fives. Fives. It's fives. 1, 6, 7, 10, 14, 18, 19, 20, 23, 25, 37, 43. Love it. Now, technically speaking, if I counted correctly, I could figure out what 6 should be, shouldn't I? Without having to ask you. You see how we can?
Yes.
Now, do you remember, I'm going to tie this back to something very, very
I don't
old.
see it
I'm going to tie this back to something very, very old. Remember how we had to divide by n minus 1 when we were calculating the sample standard deviation way back in the day? We were doing Bert and Ernie, and we had to divide not by n, but by n minus 1. A formal mathematical reason why it was n minus 1 is, since the average was already in the calculation, you're subtracting from the average, you already know something about the data. In particular, you know its sum. You know how many data points there are. I know how many data points there should be in this distribution, don't I? 10 times however many of you there are. Does that make sense? So if I do that, if I do 10 times how many of you there are, that's how many rolls we should have done. Does that make sense? So assuming I counted all these correctly, which is not a good assumption, assuming I counted all these right, all I would have to do is take that number and what? Take these away, and whatever's left is how many 6s there were. I couldn't do it here, because there's 2 left. But since there's only 1 left, and I know theoretically the sum that these sum up to, I should be able to do it that way. I don't trust my addition, though. And I'm sure I screwed up at least in a couple places in there. Hopefully not too badly, but I probably screwed up so bad that it compounds. So let's just count. How many 6s did we get? How many 6s? How many 6s did we get? All right, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Cassidy, you got 4? You got 3. 4. 16. Crap, hang on, I gotta count again, I lost count. Count them up again. We got 8, 10, 11, 13, 14, 16, 18, 21, 23, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38! Hot damn.
Well, that's weird.
I screwed up somewhere. I mean, I screwed up somewhere because it should end, if I add those up, it should end in a 0. Because I did 10 times your number of trials. So if it doesn't, so I screwed up somewhere, but whatever, it's fine. What does it add up to? Let's see how far off I am. What does it add up to? 15, 21, 11 is 33, yeah? That, 6, 11, 14, 21, 24, 243?
42.
42? Carry too many. And we've got 7. Yeah, I'm off by a bit. It's all good. Let's assume I screwed up uniformly across all 6 categories. Let's just make that assumption. I think it'll be okay. And even if I didn't, we can take care of it via technology, which is kind of the reason we invented technology, was to help us do stuff like this. David's like, man, you really can't add. No, I cannot, sir. It's one of the first things they unteach you when you work on your master's degree. Here's how to forget how to add. So here's the first thing I want you to do. Suppose you've got the die in front of you. On average, what do you roll? If you had to wrap up this whole idea with an average, what do you average? On average, what do you roll? What do you roll? Go ahead and use your TIs for this. Of course, use your TIs for this. Yes, please, please. I'm going to go back and not use the TIs momentarily. But for right now, use your TIs. This is messy. This is messy. This is real data. This is what computers should be used for. So on average, what do you roll? I'm going to enter the data too while you guys are crunching away. And I'm going to give you a picture of what you did.
Do you want us to do that as personally or as the whole class?
The entire data collection, Carly. Yeah, use the data. It's good data. It's good data.
What, like 3, the whole?
If you had to wrap up that whole experiment with one average, and maybe it's standard deviation, what the hell, right? Probably do standard deviation too, since you get it for free anyway. What do you end up with? I'm going to enter the data. Yeah, look at that's gorgeous.
3.5.
3.5.
Vote for 3.5? You guys for 3.5? Hang on now. Let me catch up.
Hurry up.
Sorry. Damn.
It's like me doing the project with this.
Yeah. Come on, hurry up.
I'm going as fast as I can.
Okay, alright, so here's that. Let's take a look at it. I'm curious. Oops, zoom there. Alright, let's clean it up a little bit. I hate that window. I hate that equation too. 1 to 7 by 1. There's your data. Freaking beautiful. Let's make that 0. That's nice. Nice. Guys like your 2s and your 5s. I just did a quick histogram and then I finagled the window. If anybody's hitting Zoom 9 to get a quick window, you're probably getting something different with gaps in it.
Yeah.
When you hit Zoom 9, you get this. The TI, remember, tries to always make 7 bars. I don't know why, it just does. That's when I start going in and finagling windows. That's where I hit the window button, and I realize, okay, the smallest we can possibly roll is a 1. So I'm going to leave that X min at 1. X max, it seems like we should make it 6,
But you want to see the
but
extra.
I make it 7 because we have to have it room for that bar.
Right.
And then I make, this is the problem right here. This is the true problem, is that. Make the scale 1. That way each bar is 1. 1, 2, 3, 4, 5, and 6. And then once you have that, you can just hit graph and then you get pretty much the same graph we have up here. So here you have X is pips, 2, 5, 6. You got a frequency here. If you need to add a frequency axis, you can. There's no need to do it right now. You guys have an average for me?
3.45.
3.45? Call that 3.5. Got a standard deviation for me?
1.7.
Average number of pips. 3.5. I want to put approximately because it's not. And then, Joe, your standard deviation?
1.7.
Now 1.7. We in agreement with this, friends? Sorry about that. Sure we can all. Whoops. Comma. There we go. There's our 3.5 and our 1.7 for standard deviation. This distribution's a fun one. This is the first one we've seen that looks like this one. It's not bell-shaped. It's not bell-shaped at all. No matter how you try to graph this, you're not going to make it bell-shaped. Do you know what this distribution is called, or what type of distribution this is? Describe it for me. First of all, let me ask 2 questions. We're going to take a break here. Why is this higher than this?
Because we rolled more 2s.
Good. That's a good answer. So, let me ask a different question then, Nick. That's the perfect answer because we rolled more. Dude, that was awesome. Yes. Does it bother anybody that the 2 bar is higher than the 1 bar?
Yeah.
Joe says yes. Nick says no. I like that. Give me why yes, Joe.
They should all be the same
Does everybody hear what Joe just said? They should all be the same height.
over time.
Oh, and then he caveated with over time. Oh, I like that, Joe. Oh, that's so nice.
This is just
So,
one-
yes, they should. Right, this was one snapshot of between 242 and 270 rolls, which I counted roughly correctly. But assuming I screwed up evenly across the counting, those heights are going to be about relatively the same, right? Good, good, very good, very good, very good. But we should see as many of this as this, as this, as this, as this. These should all be the same, theoretically, over time. Let's come back to that over break. This is called a uniform distribution. Anytime you've got a distribution where all the bars are the same heights, it's called uniform. Now you deal with this, you've dealt with this every day, probably since you were teeny tiny. You ever used a coin to decide something?
Yeah.
That's a uniform distribution, isn't it? You either get heads or you get tails, and they're equally likely. Every time you throw a die, it's a uniform distribution, because you have 6 outcomes, all of which are equally likely. Does that make sense? If you take a deck of cards, and you pull a card out and you check the suit, that's a uniform distribution. 4 outcomes, 13 cards of each. If you pull a card out and check the number, that's a uniform distribution. 13 ranks. So anytime you've got a series of outcomes across the bottom here, and then the same, arguably the same height above the top, it's a uniform distribution. After the break, let's take 5. I want to come back and I want to explore that probability, that likelihood. I want to explore that more, because that's going to be fun to talk about, I think. And we can take care of Joe's overtime. Thank you for that, buddy.